Great. Well, this is 2:30, so we'll go ahead and hop into our subject today. I'm working on grading the test right now. I will have them back to you. I'm going to mention I'm contemplating, I'm still working through grading them, but I'm thinking of taking the 2 worst questions on the test and throwing those out. So whichever ones were like you scored worst on, those are just going to be ignored. So that's probably what's going to end up happening. So yes.
Like on everybody's test, like if I did work on 14 and 15, it would be like my 14 and 15 is different, or like on average, the worst questions are taken.
No, it's going to be your 14 to 15 taken out. So not the average worst ones, the ones that were worst for you in that particular case. Which as of right now looks like a couple of the first impressions questions for most people. We'll see. I understand. No, it was number 10. That would have taken a little while. So we'll see I'll see what I can do there. Try to make it in the future. So anyhow, let's go ahead and get started. So we're going to move on to a new chapter today. And we're going to be doing chapter 8, which we're just going to be taking a couple days here for. Chapter 8 is called Further Applications of Integrals, which the reason it's called Further Applications is because we've already done an Applications of Integral chapter in Calc 1. If you remember doing the volumes of the disk, volume of shell, doing those methods, that was kind of our first attempt in working with these. But now, when we're introducing these concepts, these are things that are involving a lot more of these harder integral problems. So that's why we had to wait until now to do them. So the first thing we're going to be talking about is arc length. Okay, so what we mean by arc length is I have some curve like so. And I want to figure out the question about arc length is saying how long is my curve from here to here? Not just taking a line and kind of stretching it over and seeing how far that is, but actually how long this line is. If I travel this way, how far do I travel? How long is that? Right? And so in order to find this, of course, we need to set up a way to work this out. We need to set up a way to find this because I can't. I mean, it's hard with a curve like that. You'll just be like, oh, it's clearly this equation, right? So the way we're going to do this, right? As I said, maybe just trying to take one line and stretch it all the way to the end is not the greatest idea. Okay, that's not really going to tell us a whole lot. But what I can do instead is I can take tiny line segments each point, which colors is there another? Let's see. Yeah, they're all gone. They all got. That's there. We're going to take smaller line segments, like just connect 2 points as I move along. So here's one line segment, here's another line segment, here's another line segment, here's another line segment, here's another line segment, another, right? And I'm going to take all those different line segments and add them up, right? And that's going to give me an estimate of my length, right? Now, my ultimate goal, of course, is to get what it actually is and not just what it approximately is, right? So, right, what we have written right now, right, is I have, I put a few dots here, but let's say we may have in total points, right? And we're going to say that the length of this portion that I drew is approximately, we're going to take a sum here, and it's going to go from I equals 1 to n, right? So we're going to say, right, so this is P0, P1, P2, P3, all the way up to Pn here. So we're going to take the sum of each of the length of each of these line segments, which I'm going to denote as pi minus 1 pi. Okay, the absolute value of that. So that is just saying the distance between those 2 points, the distance between pi minus 1 and pi. So we have p0 and p1 line segment, p1, p2 line segment, p3, p4 line segment, etc. Right? Now, right, ultimately, I don't want to work with this. We're talking about integrals, right? So we want to get this to an integral somehow, right? But in order to do that, I need to have a function, a clear defined function in here. I need to have a delta x, right? Because that will give me what I need to construct my integral as I go towards infinity, okay? Which it should be noted that if I did take this as I went towards infinity, right? If I had infinite points on that line, then the length of this line would actually be the limit of this. Okay, so let's work through this now. So let's say that I have 2 points, right? So pi minus 1, and this is going to be x. So we're going to have xi minus 1, yi minus 1, right? So that's that point. It's got a certain x and y coordinate attached to it. And then we're going to have point pi, which is going to have xi. Okay. So if I want to know the distance between these 2 points, right? How do I find that? Do I know how to find the distance between 2 points on a line? Yes, how? What is it? It's minus actually. But, Yep. So normally, yeah. So we would say y2 minus y1 squared, or y1 minus y2, doesn't matter. And you could also do x here as well. It doesn't matter which order. I might put x here, and then I might put y here. But then I'm going to use these points in particular. So I'm going to have xi minus xi minus 1 plus yi minus y1 squared. Okay, so that is the distance between these 2 points. This is our pi minus 1 pi, absolute value. Okay, so this is what we're adding in each case to get that way. Okay, now, right, let's think about this. We want to, whenever we're picking these points, right, we kind of want to have them evenly distributed, right? So we want to say that in each case, the distance between PO and P1, I want that to be delta x, right? I want that to be a certain length. And the distance from P1 to P2, I want that to be the same delta x. P2 to P3, delta x. I want them to all be the same length. And so what that means for us is that this xi minus 1, I can just write as delta x squared. Okay, because that's just the difference between the 2 x's together. Similarly, although we have to be more particular, right? Because our y's aren't always going to be the same distance apart. They're going to change depending on where you're at, right? Like these p's are farther apart than these p's are, right? Just based on how the curve is. So we're going to have delta x plus delta y pi squared. So maybe I'll write it like that. Let's see. Okay, but this is kind of what we're working from. This is what we're going to use to get us to where we need to go, right? Okay, now let's bring back an old friend to help us out real fast. Who remembers what the mean value theorem is? Anybody? Who remembers? You're close. That's Rolle's theorem. But Rolle's is used to prove the mean value theorem, which says that, and I'll just write it like what you would have seen. So this is the mean value theorem. This is, right, my kind of the equation for the slope of the secant line, right? if I take y2 minus y1 over x2 minus x1, right? And this is the derivative, right? What the mean value theorem says is that there's going to be some c value in between a and b if the function is continuous, such that if I take the slope between those 2 points, then f prime evaluated that c value is going to be the same, right? So just saying here, I'll give you kind of a pictorial example so we can remember. Right, if I'm saying from this point to this point, right? So this is my A point, this is my B point here. What this says is that the slope of this line, there's going to be some point on my curve such that the slope of the tangent line to that point is going to be the same slope, right? And so that's what we're talking about when we use this. Now, this is going to apply here because I want to, my ultimate goal is I want to try to rewrite this delta yi in some way because I want to be able to get some information from it. Okay. And so what I'm going to do is I'm going to take f of, right, so in each case, yi minus 1 is equal to f of xi minus 1, right? And yi, right, just keep that in mind. We have some specific function in mind here that we're finding the length of. And so y is related to the x in that way. It's not just some random x, it's some random y you think, right? Y is dependent on whatever the x is. Okay, now the mean value theorem says that if I take f of xi minus f of xi minus 1 over xi minus xi minus 1, and this is equal to some f prime of, and the book uses xi. Okay, so there's some value. So xi star is in between xi and xi minus 1. That's going to give us this sort of situation. Okay, and again, the reason I'm doing this is to label this in terms of my function, so I can have some sort of general statement to use. Okay, now xi minus xi minus 1. What did we say that was? Delta x. Right, and f of xi minus f of xi minus 1, right? That's the same thing as yi minus yi minus 1. Right. Well, what is yi minus 1? It's delta yi, right? So this says that delta yi over delta x equals f prime of xi star. So some value in between those two numbers, which so then we can finally write that delta yi equals f prime of xi star. Okay, so I've written delta yi in a form that I can more easily use it. And so I'm going to take this thing, I'm going to substitute it in, and maybe I'll bring that up here. So I'm going to have, so my length now, or sorry, my pi minus 1, or it doesn't matter which way you write it. It's the same thing. Is equal to the square root of delta x squared plus f prime of xi star delta x. Like this. Okay. Now, what do both of these things have in common with each other? They both have a delta x in them, right? So this is the same thing as, and it's delta x squared inside the square root times 1 plus f prime of xi star squared, which then I can take the square root of this delta x, which is going to give me square root of 1 plus f prime of xi star squared delta x. So we get this. Now this is really good, okay? And the reason being, right, remember I said earlier that if I'm gonna use integration here, I need to have some function times delta x. But that's exactly what we get. Okay, so this limit becomes a limit as n approaches infinity of the sum from I equals 1 to n of, and we just found that this is equal to 1 plus f prime of xi star, depending on what I is, depending on what change, times delta x. Okay, so we're left with this. Okay, this is fantastic. Now, notice we can take this now and we can transform into an integral, right? Because this is exactly the form of Riemann sum that we're familiar with, right? And when it comes to the Riemann sum, right, we take the function inside, right? And depending on what delta x is, which we wouldn't, delta x is going to be dependent on obviously whatever your a and b are going to be in this case. I can take this thing and put it in the terms of an integral, which is going to be the integral from some a to some b, right, depending on where you're going, of the function, which is in this case is the square root of 1 plus f prime of x squared, and then that's ultimately going to become. So we change kind of the xi part to just x. Now this is okay, right? Because let's think about, because you might be wondering, well, does this is like depending on which kind of integral we're working with. So does this, can I just do this? And the truth is, right, let's think about if I'm taking my n as it goes towards infinity, right? I'm picking infinitely many points, right? So what's happening to my delta x in each case? If I keep adding more and more points in, is my delta x getting bigger or smaller? It's gonna keep getting smaller, right? Good. It just keeps shrinking on itself. And so the interval is going to get to a point as you go towards infinity where it's nothing, right? It's basically just 1 point in a way. And so this xi just kind of it like there's only one choice in the end when you take it. And so okay. Now this is the integral we use to find the arc length of the curve from point A to point B. Okay, and this is exactly the equation we're going to be using in some examples. I'm going to practice and just see how it works. All right, so good. We'll go ahead and start doing some here. Any questions thus far on this? Okay. Hopefully the kind of the structure of this makes sense where this comes from. Obviously most people aren't going to think first to try to bring this into the picture, but it does help us to really bring everything together. Questions? No? Okay. Good. Let's do an example. Okay, now you're going to find when you do the homework problems that there's going to be like a couple, like the first ones that you're assigned are just going to say to set up the integral. So you're just going to set up how it would work, but you don't have to evaluate it. The reason is that we just don't know how to. We can't evaluate it. But it still kind of gets the idea across and what we're going to do, right? So I'll start with that first. So we'll do, so this is, I'll just do the problems because again, these ones are really hard to come up with neat examples for. So number 4, we're just going to set up this integral of what this length is going to be, right? So it gives us, so it says find, so set up integral, find length of curve. And the curve that it gives us is y equals x e to the minus x. And this is going to be from 0 Okay, so this is the problem we're working with, right? So, as we just determined, the length of that curve is gonna be this equation, right? So we wanna find our L here, which is gonna be the integral. What's my A and B in this case gonna be? 0 and 2. Yep, absolutely. It's just the numbers that they give you, right? 0 to 2 of the square root of 1 plus, and I'll go right f prime now. Plug it in. So f prime of x. Okay, so notice I'm not plugging f in here. I'm plugging in f prime, right? So I need to plug in the derivative of whatever f is, right? So let's work through this real quick, right? If y equals x e to the minus x, what is the derivative going to look like? How do I find the derivative of this thing? Product rule. Good. So product rule says, what do I do? Okay. Great. It's just one, ends up being 1 times e to the negative x. Good. Plus, and then here we just do the opposite, right? So we're going to leave the first one and then multiply by the derivative of e to the minus x, which what's the derivative of e to the minus x? Yep, that negative is going to come out, okay? And so we're just left with e to the minus x minus x e to the minus x as our derivative, okay? Now this is precisely what I plug in here. So 0 to 2, the square root of 1 plus e to the minus x minus x e to the minus x squared dx. Okay, and if you want to square that, you can. It doesn't really do a whole lot, but this is the integral. Okay, so doing this integral, right? If you find a way to do it, will give you the length of that curve. Okay, it's as simple as that, right? The work might come sometimes to like really think about, can I simplify this in some way? But for some problems, you just have to simplify it. Okay, and so that's all beta. Any questions on this so far? I mean, this is basically the formula they're going to be using this whole section. You just keep plugging into it. Okay. Make some room, and we will do some. Okay, let's do, let's see. So I give you the some even ones to do, so we don't want to do those ones. So let's start with number 12. Well, actually, maybe not. I'll do number 14 first. Okay, so number 14 again is we're going to find the actual arc length in this case. So we're not just finding we're not just going to find, oh, what's what does it look like, but we're actually going to evaluate it and get the number out of it. Okay, so the function in this case is going to be the natural log of cosine x, and this is going to be from 0 to pi over 3. Okay, so maybe before we get started, we know we need to get the derivative, right? So let's just go ahead and find the derivative of this, right? So I want the derivative of the natural log of cosine x. So how do I do that? Not 1 over sine. It's 1 over. It's going to be 1 over cosine, right? Because you need to start off right now. The derivative of the natural log of x is 1 over x. So we take whatever the thing is on the inside and put it at the bottom. But then I multiply using chain rule by the derivative of the inside, which what's the derivative of cosine? Negative sine. Good. Okay. What's sine over cosine? Negative. So our length now is going to be the integral from 0 to pi over 3, right? Again, you just use whatever A or B they give you, of the square root of 1 plus negative tangent x squared. Okay, is everyone following on this at this point? Right? You just plug in the derivative. Okay. So this is going to give us 0 to pi over 3 of the square root of 1 plus, what happens to this negative inside? Where it just disappears, right? It doesn't matter. So we're going to get 1 plus tangent squared x. Okay. What do we know about 1 plus tangent squared x? Secant squared x. So we get the square root of secant squared x, right? Which of course, the square and the square root cancel each other. So we're left with the integral from 0 to pi over 3 of secant x dx. Do we know how to integrate secant x dx? Good. Got it. Yep, so it's the natural log of secant x plus tan x. We're going to evaluate this from 0. So let's kind of plug things in here and think about what we're going to get. If I plug in pi over 3, right? Do we know what the secant of pi over 3 is? Maybe. Or how about what's the cosine of pi over 3? Cosine of pi over 3? What is it? Not radical 3 over 2. Not radical, yeah, it's 1/2. It's not radical, you're close. You guys were working your way down. It's 1/2 in that case. Okay. So sine of pi over 6 is 1/2 and cosine of pi over 3 is 1/2. They go the opposite direction. Okay. Tangent of pi over 3. Let's think. So maybe let's ask the question real fast. What's sine of pi over 3 going to be? Root 3 over 2. This one's root 3 over 2. Yeah. Okay. So if I want tangent of pi over 3, yeah, just root. Because I take the square root of 3 over 2 over 1 over 2. The 2's cancel each other out, so we're just left with the square root of 3. Now, do I know what secant of pi over 3 is going to be? Not, it's 2. Yes. Right? Because secant's 1 over cosine. Oh, wait. Secant's 1 over cosine. And so we just get 2, right? Because it's just 1 over 1/2. Okay? So secant of pi over 3 is going to be 2. And tangent of pi over 3 is going to be 3. Right? Now, now let's think about secant of 0. What is secant of 0 going to be? Do we know what the cosine of 0 is? Okay, so what do you think the secant of 0 is going to be? It's also going to be 1, right? Because it's 1 over 1. What's tangent of 0? What's sine of 0? 0. So if it takes 0 over 1, what do we get? Still 0. Okay, so we have the natural log of 2 plus root 3 minus the natural log of 1 plus 0. Well, what's the natural log of 1 plus 0? Not 1. It's the natural log of 1, right? Because 1 plus 0 is 1. What's the natural log of 1? It's 0, not e. You're thinking the natural log of e is 1, but the natural log of 1 is not. It's actually 0. Okay, so just keep that in mind. So the 0 one just makes the whole thing 0, right? So in the end, we're just left with the natural log of. Okay? How's that? Good, makes sense? Yeah. Okay, now, you may, you're gonna run into some problems, right? Where, for example, and this is why I wouldn't do this one after, but you might run into some problems which have something like x equals y to the 4 over 8 plus 1 over 4 y squared, and where 1 is less than equal to y is less than equal. Okay. Now, the reason why this one might be interesting to think about is because it's not y equals x. We now have x equals y, right? And your first instinct might be to try to solve it, but that's not. I don't even know if I could solve that for y. I wouldn't advise you to try to solve that for y by itself. This is actually completely okay for us to do. And the reason being, right? Maybe I'll just show you using a little trick here. Let's think about this, right? So let me take. So let's take my length integral, right? Well, actually, let's just think about the interior, right? So let's think about that square root of 1 plus f prime of x squared dx on the inside, right? Now notice f prime, right? Depending on what, this is the same thing as dy over dx, right? If y equals f of x, then I can write f prime as dy over dx. These literally mean the same thing, it's just different notation. Okay? If I bring that in here, I get something like this, right? Which doesn't seem very remarkable at the moment. But what I'm going to do now is I'm going to take this thing and I'm going to take this dx and I'm going to bring it back inside, right? And we'll see why in a second. So I'm going to take my 1 plus dy over dx squared, and then I'm going to bring back that dx inside, which is going to be dx squared in that case. Okay? If I take this dx and I multiply it to each of these terms, right, I'm going to get dx squared times 1. Simply this dx squared, right? What's going to happen if I multiply dx squared by dy over dx squared? It's dy squared. The dx is just cancel each other out. So I get this thing. Okay? Now what happens if I take this thing and instead of taking out dx, I take out dy? So I'm going to take, so I'm going to do this. Okay, so instead of taking out the dx squared, I'm just taking out the dy. If you want to check it, it's still the same thing, right? I haven't changed the problem. But now what's going to happen is I can take the square root of this dy, where I get the square root of, and I'll rewrite this in a more formal order what we're used to. Okay. And I get this. Maybe, let's say that instead of having a function of x, I have a function in terms of y, right? This is the same thing as, well, actually, maybe I'll just do it. So I get this thing, right? Which says this is the same thing as this guy, right? So if I'm going to find the arc length of whatever the f of x was, right? But I'm given x in terms of y, that's okay. I can still work it out. All I have to do is just take the derivative of this function instead of taking the derivative of it to whatever f of x would have been in that case, right? So all of that to say, this situation, nothing changes. Okay, the only thing that's going to change is that instead of a dx on the end, you're going to have a dy on the end. Okay, so the length in this case is going to be the integral. What's my a and b? Going to be 1 and 2. Yeah. Of the square root of 1 plus, and we're going to do f prime of y, right? Just take the derivative of this function, right? Because again, what we just showed here is that it's the same thing. Nothing's going to, it doesn't affect the problem that I'm doing it a function of y instead of a function of x, except that it's, so I get this, okay? So if I have y equals f of x, you know, do what we have been, and if you have x equals f of y, do the same thing, except you have y's instead. Okay. So let's talk about our function, right? I want to take the derivative with respect to y of y to the 4th over 8 plus 1 over 4 squared. Okay. So how do I take the derivative of this thing? What's the derivative of this term going to be? Good. So it's 1/2 y cubed, because again, and I want to reiterate this because I want to make sure everybody's listening. If I have a constant, right, like 2 in the denominator, 8 in the denominator, or I have a constant in the numerator, I don't have to use product rule. I don't have to use quotient rule because they're just numbered, right? You can just set them off to the side. Okay, it's going to save you a lot of work. To just remember that as you work through, right? So what happened is we took the derivative of y to the 4th, which is going to be 4y cubed. The 4 over 8 is 1/2. Okay, so that's where the 1/2 y cubed. How about the derivative of this part? Right. So how do I need to work this out? Right. So this is the same thing as 1/4 times y to the negative second power. And now how do I take the derivative of 1/4 y to the negative second power? Yes. So we get this, or I can write it as 1 over 2 y cubed minus 1 over 2 y cubed. Okay. Fantastic. So this is my derivative, and so this is exactly what I'm going to take and plug it over here. Where I'm going to get the integral from 1 to 2 of the square root of 1 plus, and I'm going to write it as y cubed over 2, okay, minus 1 over 2 y cubed squared believe it or not, this is still possible for us to solve very much, but set up particularly so we can. So let's kind of think about it, right? What's going to happen when I square that term out, right? So I have the integral from 1 to 2 of the square root of 1 plus. Okay, so let's square this thing. So help me out. How do I take y cubed over 2 minus 1/2 y 1 over 2 y cubed and square it? So we're gonna have y to the 6th divided by 4, right? Because we take this term and we square it. Again, you can write this out in full if you want, or you can just remember you square the first term and then you square the last term. So what's the last term squared? One over 4 minus 6, right? You have to multiply the 2 by itself as well again. Okay. Now in the middle, right? I take the 2 terms and multiply them together, and then I multiply by 2. So what happens when I multiply y cubed over 2 times 1 over 2 y cubed together? You get minus 1/4, right? So let me show that here. Times, and then we have to keep that minus as well. So we're going to get the y cubes are going to cancel out. So we're going to get minus 1 over 4. But again, that gets added twice because of the FOILing. So we multiply by 2, and we get minus 1/2. Okay. Now, I can take this 1 and this minus 1/2 and put them together at least. But I'm not gonna put them together on the left side. I'm gonna just add the 1 to the minus 1/2 and keep it in the middle, and you'll see why. So y to the 6/4, what's 1 minus 1/2? So I get this. Okay. So what I want us to do in this very moment is I want us to focus on this and this. Okay? They're exactly the same thing, except this one has a plus in the middle. Okay? The reason that that's significant is because this is exactly what I would have gotten if instead of this being a minus here, it was a plus. It was a plus instead, right? So that's something you really want to think about, something you want to keep track of. Because since these are so similar, you can say, oh, well, this is just going to be y, right, y cubed over 2. But instead of minus, it's going to be plus. So this is a perfect square, and this is what it is, okay? It's exactly the same thing as this guy was, except it's got a plus instead of a minus. And we can see that because they were the same expression, except one had a plus instead of a minus, right? Does that make sense? In some way, shape, or form? Please ask questions, like I can explain it more if I need to, of course, I don't mind at all. You're gonna have a couple problems like this. There's one on the mandatory homework like this. So I just want to be very clear that we understand what happened, okay? Right, so again, bring your attention to the similarities between these two and notice that they're the same aside from, you know, this one had a minus, but they just put a plus instead. Okay, good. So what's going to happen to this square in the square? Cancel out. I think I heard someone say pancake. And we're going to get y cubed over 2 plus 1 over 2y cubed. So now I can take the integral of this thing. Okay, square and the square root cancel out, so I'm left with this thing, and I can integrate this. Right. So let's do that real fast. I'll keep this isolated. So. Okay, so how do I integrate y cubed over 2? And then just like before, we want to take this and rewrite it as y to the -3rd over 2. So how do I integrate y to the -3rd over 2? Right, -1/4 y to the -2. And then this 1, 2, which of course I can just write as 1/8 y to the 4th minus 1/4y squared, or put the y to the 4th up there, doesn't matter. Okay, now notice, funny enough, this is almost the function we started off with, except the sign just changed to a minus instead. Okay, you can't just do that though. If you know that's what's going to happen, I don't want you to just write this. Okay, I need you to show me the work. I need you to show me you understand. Okay, no shortcuts here. Okay, so if I take 2 and maybe I'll write it kind of say on top. Okay. What is, so we want 2 to the 4th power over 8 minus 1 over 4 times 2 squared. Right, again, just plug it in my numbers. Minus 1 over 8 minus 1 over 4. Okay, so what is 2 to the 4th power? Anybody? 16 over 8. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. Minus 1 over, then we have 4 times 4, which also ends up being 16. Okay. Minus 1 over 8 plus 1 over 4. Okay. Now we'll have to do kind of a little bit of work here, but what's 16 over 8? 2. Right. And then I'll get the common denominator here, so we're going to get minus 1 over 16 minus, how can I, if I want to make all of them 16, right? What do I need to multiply this one by? 2. I want to get the common denominator here, what I multiply it by? 4. Thank you. So we're going to get, so negative 1 minus 2 plus 4 is what? Negative 1 minus 2 plus 4? 1. So we get 2 plus 1, 16. Which from here to, I would want to get a common denominator, which would give me 32 over 16 plus 1, 16. Good. So this is the length of this curve from y equals 1 to y. Yes.
So when we have the square root of y plus that expression, how to just take this out.
We cannot do that, right? What I think what you're trying to say is, could I, if I had this, could I just do this? So you're trying to say, yeah, this is not a rule we can use. That's incorrect, right? And if you want to see real quick why, if I gave you this problem, square root of 9 plus 16, what is 9 plus 16? 25. So this is supposed to be the square root of 25, which is what? 5. However, if I say, let's just take the square root of each one, I get the square root of 9 plus the square root of 16. Well, what's the square root of 9? 3. And what's the square root of 16? 4. Plus 4. 7. They're not the same. Okay? So no, you can't shortcut and just take the square root of each piece. You have to, the only way this is going to work is if you can take it as a whole, right? Which we ended up being able to do. Okay, but I can't just split up the square root. That's why we need to think of like trig substitution, right? Because if we could just use that, then the 1 minus x squared case wouldn't matter. We could just do square root of 1, square root of x squared. Okay. Good. So there's a couple of examples for you. You can really think about. Most of them again are going to fall into the same vein. I don't want to like go through every possible scenario with this. You can feel it yourself. These are probably, it's good to do this one because this is probably like the hardest in terms of like just it not being clear at first of what you're supposed to take. So that should help you there. The last thing this section talks about is just takes it just takes my arc length and it turns it into a function, right? So it says, which is just useful in some cases, we have the function s of x equals the integral from 0 to x, or sorry, from 0, it's from a to x, square root of 1 plus. Okay, so this is called the so this is just something that pops up, right? Obviously, this just says given a function, right? Then this is the corresponding arc length function for that starting from point A, right? You have some sort of starting point, and then you work from there. which generally is possible. If you do work with one like this, it'll give you that starting point. And then from there, you can sort of evaluate and see what the arc length would be in general, right? Because in the end, all I do is I just plug in A. Now, the reason this is significant is it just gives us kind of a neat little naming scheme and notation, right? Which I'll explain here real quick. If I take the derivative of this function, what is the derivative of this thing going to be? If I take the derivative of this arc length function. What do we think? Okay, so I got an integral. Good, it's what's inside the integral, but you just put x instead of t. So it's just square root of 1 plus f prime of x squared. Come on, guys. This is the first part of the fundamental theorem of calculus. Something you need to carry with you, you need to know, right? To take the derivative of this thing and take this, right? And from this, if I take both sides and I multiply it by dx, okay, I get that ds x is going to be square root of 1 plus f prime of x squared. Okay, or you can just ignore this x here together and just say ds equals this, right? So if you're given a problem, right, where you might see something like this, what this is saying, what this is telling us is that I'm working with the arc length, okay, but they do it in terms of mass, right? Now, again, this may not seem like something that's significant to you right now, but for any of you who do end up taking Calc 3, which I imagine a few of you will, this is extremely critical because whenever you go to 3 dimensions, even in 2 dimensions, but especially when you go to 3 dimensions, you're no longer just taking an integral, you're no longer working with functions from, like just from the axis up to the curve, but you might be working with something, like you may not be going to the axis itself, but you may be doing it with respect to some curve, which I know is a little weird to think about, but they'll write these things in terms of like ds here. So it's in terms of whatever that arc is. Okay, and from there we can kind of plot it. But thought it was worth mentioning. There's some example problems. There's like one example problem that just says to find the arc length function, which is just more generalizing doing the process we have here, right? Except instead of having a number up top here, you might have x instead. So you're not going to be getting a number answer, you're going to have some function to respect. That's all it is. Okay, so from there it's very okay, cool, great. Any questions for me? We're doing pretty good. Maybe if we get to the next section, I'll let you guys know. Or see how we do. Anything? Okay, cool. Well, I'll give you 10 minutes. When that clock hits the 7, basically 4:35, and we'll keep going after that. So. No. No, it's not represent. You could probably I mean, Our sign would be like a neat function to plug into this, doing the arc length, because it works out nicely, I think. If you kind of bridge everything together, I guess I'm not 100% sure on that. Yeah, they're not necessarily related though. The arc and the arc sign is different than the arc that we're talking about here. Like, I mean, I guess, I don't know. It more indicates like the inverse, like going the opposite direction. They just use arc to, instead of doing the negative ones.
So how there's like a line segment, you have from point to point. So it's function. That's the line.
So the definition of it, so just take that definition, right? And say, like you take that infinitely many times along a curve, which obviously you wouldn't talk about it that way. You would more say it's if I took my curve and I stretched down through a straight line, it would be the distance between those 2 points, right? But it is made up of the way you find it is doing all those individual